Okay, so for this last lecture tutorial regarding my presentation, we will today focus on the global evaluation of performance of a PV central that we call performance ratio. As I previously introduced that to you, I said that it is a key parameters to see if the PV central is in a comfortable operating condition, is operate well, or if there is a problem. Okay, so it's important to have an idea of this performance ratio. There is here today we will mainly focus on the impact of some parameters on this performance ratio, internal parameters, so parameters that are linked to the PV central. Okay, at which stage we could lose some power internally to the PV central. But there is also external factors that can impact this performance ratio. That is could be the soiling, for example. Okay, soiling effect. Okay, before I will just introduce the startup that I'm a co-inventor and that has been created in 2019. And the purpose of this startup is to be able to identify if there is a problem on a PV central, just analyzing the signal. So just analyzing the power which is generated, the power before and after the inverter, okay, and to be able to identify if there is a problem. But if there is a problem, is not the more difficult thing. The more difficult thing is to identify the origin of the problem, okay, and then we will do the tutorial. So the startup, which is going a spin-off from my laboratory, so is Heliocity. The main objective of Heliocity is to focus on integrated PV central, so at the scale of city. And city is a kind of extreme condition for operating because the temperature is usually higher in the city than in the rural area. Okay, we have seen yesterday why. There is pollution. Okay, so pollution means a kind of filter around the atmosphere. Nebulosity of the atmosphere is not so clear. And soiling means pollution means also potential soiling of the PV panels. Okay, different aspects. You have also shadow. It's stupid, but if you are installing your PV central and then few years later there is a building, you could have partial shadow and it will not operate very accurately. The other main problem is that the maintenance, you don't go every day on the tower, the roof of a tower to see if everything is okay. It's more difficult to, in the urban, where most of the PV centrales are on the roof, less accessible than in rural when you have a full field of PV panels. Okay. So it has been created in 2009. Now the startup is in Grenoble, so it's at 50 kilometers from my place, from the Ines. So you see, it's also a mountainous area. And so the objective is that a lot of things can impact. So here you can see some snow, some partial snow. That means that there is partial shadow that will impact the wool production. You have the bird, of course, that create some dust, okay? Even if it is local, okay? You have a problem because you have a shadow point on your cell, okay? So usually we find that in cities, the performance that are real compared to what is expected is under of what is expected, or around 15%. So it's important, okay? So it's important to identify the reason why, okay? So the principle is to develop the product that is sold is a software as a service, okay? SaaS. The software as a service is consisting to provide information about your PV central. Behind it is a combination between the modeling of the PV central. The modeling, we know a lot of different BIPV integration, facade, roof, on insulation, on a air gap, and so on and so on. So this is a pattern that is behind between the modeling and the analysis of what is provided by the PV central. So there is a period of learning, okay, to see if the model is consistent with the PV central. And after maybe 2 weeks of learning, then it will compute that permanently, okay? And as soon as there is a discrepancy, that means that there is something wrong, okay? Something wrong that could be linked to the PV central, a cable which is cut, dust on the PV central, or from the surrounding. That means that maybe there is a building construction in the surrounding. Maybe there is a crane which some few hours during the day generate shadow on the PV central. Okay? So first it consists to have a kind of audit of the PV central. As I told you, the performance ratio, for example, what is a good performance ratio? That means that you have no worries to have. You remember the value? It was 80%, 0.8, okay? If the performance ratio is at 80% or more, that's good, no problem. If it is under 80%, that's not so good. There is a problem. The problem could be since the beginning, because the PV has not been well integrated. What is well integrated is that you put your PV directly on the isolation. For sure, for this configuration, this PV panel will overheat. Okay, it's not absolutely not ventilated at the back side. So for sure, the temperature level will be higher than expected and the power generation lower than expected, okay? So it is some problem like this because you have to leave at least an air gap between the PV and the building. Another problem that could be a small self-shadow. That means that you have on your roof a chimney, okay, or a ventilation system, and the installer put PV panels around this. That means that during the day it will generate shadow all the day long. A small shadow, but a shadow. It's happened also to have such problems that means that since the beginning the PV central has not been well integrated. Okay, so the audit is necessary. But after, it could be also problems that appear later. And then the software as a service allow to have a continuous performance monitoring. The main issue or the main challenge was not to go, if you have a customer that have a big PV central integrated on the roof, is not to say, okay, we will monitor your PV central. We will put a meteorological station. We will stick several thermocouples. Okay, no, it's too heavy. It's just analyzing the production of the PV central without any other sensors. Okay, so it is a challenge. Okay, so it is based. So as there is no local measurement of meteo, we are basing our analysis on the PV production. It's easy, what is the power which is generated, but coupled with satellite data, okay, to have an satellite and meteorological data in order to have, of course, an estimation of the local environment. And the modeling has also considered how to transform satellite data in terms of solar radiation to local meteorological file, okay, to be exported to this PV central. Okay, so it is based on one side on physical simulation. We work during 20 years on the modeling of BIPV. I show you several examples of different facades, semi-transparent, opaque, with color, not color, density of cells that can vary. So it is the kernel of the software, okay? It's able to model a lot of variety of integrated PV central and data analysis for a time in order to to learn about the behavior of the PV central and to adjust some parameters to the physical model. So after 2 or 3 weeks of running, the tools should be able to follow exactly the PV performance. Okay, it is the principle. And then, if there is a problem, so as soon as they start to have a discrepancy, okay, that means that maybe there is a small problem that has to be identified. Okay, so it's quite well placed compared to concurrents, to similar tools. And at that time, it's quite well. I don't know if you have seen that I show you carpet plot one day on a facade. We are using a lot of that carpet plot to treat the data because sometimes if the inverter is not able to focus on the maximum power, they will have lack of data, okay? But that don't mean that there is a problem. Maybe there is something about the inverter, but so we are also obliged to first also filter the data in order to not identify errors that do not exist, okay? So it is this kind of carpet plot. I show you this kind of carpet plot for showing per day in the facade all the different level of temperature. One line was the temperature during the day. Okay, so I just finished the introduction. At the beginning of the creation, we were 3, okay? So 2 co-inverters, me and Léon Gaillard, that is a research engineer that was working with me during 15 years. Okay, now he's in the startup, he's a CTO. And the CEO is an investor that believe in the products, and now he's a president of the startup. So we were 3 at the beginning for the creation, and now the startup has around 10 people working. Okay, so developer, informatic developer for the interface, data analyst, communication. Now there is commercial. Okay, it's so if you want to go and see what it's doing, if you see some opportunity, there is a contact here. Okay, so the principle is physical model, data analysis, and to see if there's match or if there's no match. what could be the possible problem. Question regarding this? If not, we can proceed to see on a real PV central. So it is on my campus, okay? You see here, the PV panels are here, are used to protect from the sun during summertime, okay? I give the latitude, 45 degree north, longitude, 5 degree east, okay? You all the time useful to know that. So a brise soleil is a shadow, okay? It's a cut the sun. And so there are 44 photowatt modules, okay? The reference are 1200, the model. The watt peak is 115. The inverter, there is also the branch, okay? And I give you the characteristic, okay, of one module and the inverter, okay? So, I give you some question. In principle, you should be able to answer. So, regarding the specificity of module and the inverters, what is the PV module's power loss coefficient as function of temperature? And what is the average efficiency of the chosen inverter? Okay? So I'll leave you think about. So you have to read the characteristic. For the first question, so where you can find this you find that? Fine. Yes. Good answer. So it is here. The power. Of course, there is an impact on intensity, voltage, but here the question was about the power, okay? So the coefficient is minus. So that means that you are losing loss of 0 point of the power per each degrees over 25 degree. Huh? It is established here for 1000 watt per square meter, 25 degree, mass, atmosphere mass 1.5. So this coefficient means that if you are at 26 degree, you will lose 0.43% of your power, expected power, okay? Then regarding the inverter, what you can see that there is the same branch but with different range of inverter. Okay, so which one we will choose? What is important? I was.
Choose the power.
The power of it is this power peak.
115.
Yes.
Inverter power has to be more than this. Inverter input power.
Yes. So what should be the input power? (44) multiplied by this, okay? 44 modules. So I find 5 okay. So which inverter we will take? I said it is important to be in the good range because if we are below, it will not be able to follow the true track, the maximum power. If we are over, it's less important, but the accuracy will not be so good, so we will lose some energy. So which one we will take? Yes, this one. Okay, the range is between 3,500 and 5,500. So for this one, we saw that the answer to the question is 83.5. Okay, it is this. So it's a good, huh? The efficiency of an inverter, hopefully, is not bad. Okay, if you compute 115 multiplied by 44, you will find the power peak of your central that will give you the range to choose for the inverter. Okay. So this okay. Now we are looking that we never look before. Before we were just telling the irradiation for 1 month is like this. What is the global irradiation potential production for the month? So we are thinking in months, in year. Now it's at time t. Okay, at time t, we look at the inverter and it will provide us some information. Okay, about tension, about voltage, about current. Okay, so here we are at time t. So at time t, the irradiation which is coming on my plane, okay, which is measured. How it is measured? Generally, it is a PV cell. Each PV central they are not using a pyranometer. They are using a very well-known small PV cell. So with this very well-known small PV cells, we know exactly the temperature, and thus regarding the production of this well-known PV cells, we know the temperature and the radiation. Okay. So usually it's a small PV small PV cell which is put here and provide this. Okay. So at time t, we see that there is a radiation on the same plane as the module of 843 watts per square meters. We measure that the direct current voltage, so direct current voltage, so continuous, is 253, and the intensity is 14.7 ampere. Okay. On the grid side, so after the inverter, it's before and after the inverter. So you are now alternative. After the inverter, the role of inverter is to convert direct current to alternative. Okay. So we measure 231 volt and intensity of 15.1. The module temperature is at 55. It is still provided by both this reference cell that gives the temperature and the radiation. We assume that, and it is the case generally, that the connecting cable, okay, there is loss by Joule effect, and that this loss is around 1% of the power. If we find that it's more, that there is a problem. I will show you how we can see that it is more or less, okay? But generally it's around 1%.
This includes both AC and DC, right?
Hmm?
This 1% includes both DC and AC, right?
Yes, yes, yes. The global power loss. The global power loss of your system. So it's one part. At the beginning, you should estimate optimal power. And due to cable, you will lose 1% of this power, at least, due to the cable connection. Okay? We will see what is beginning expected power, and then all the loss that we are having. Okay?
So from module to inverter, it is DC cable.
Yes.
Then from inverter to grid, it is AC cable.
Yes. So it's
both.
considering both. Yes,
Both.
you're right. So, okay. So I ask you to compute the efficiency of the inverter. Okay. We have the value provided by the manufacturer. The value is 93.5. Is it consistent with the value we are really measuring? Okay, this is real value. Huh? What I'm giving to you, it was real value. One day, it was in July, I don't remember. We have this radiation, this temperature of the cell is not ambient temperature, it's cell temperature. And this is the data provided by the PV central. Okay, so it's real value.
What's the ambient temperature?
Don't know if we have the ambient temperature here. It should be around 30 degrees. 30 degree will provide
Maybe 25 we can consider. 25 we can consider.
No. We can't consider 25 because we will see that there is an effect due to the temperature, of course. I don't know if the no, not the temperature of ambience. But depending of the temperature of the cell, if you look at the lecture, we are able to come back to the ambience temperature due to what is called not velocity. Allow to go to from ambient temperature to TC, okay? Or if you have TC, you can also evaluate the ambience temperature.
One range is given, minus 20 to 50 degrees.
Hmm?
One range is given here on inverter reference table. Ambient temperature range is given.
Ah, it's given? Okay.
Minus 20 to 50.
Ah, yes, okay. Yes, but it is the operating temperature of the inverter. It is the reason why it's that in very hot country, this kind of components are put in a cooled chamber. Okay, in the desert, for example, if you are you will put that in a room. If you don't cool this room, it could be over 50, so it will not work very well. So unfortunately, you are obliged to cool this chamber where you put the inverter, the battery. It's better for lifetime of these components. Okay. So usually, yes, in very hot countries, they are put it in a small house, in a small chamber, which is cooled. So part of energy which is produced by the PV central is used to cool the electronic device. Okay. So did you compute that? What I have to do? So I can call that efficiency of inverter. But you have to make the ratio between what you have before and what you have after. Between what you have after and divided by what you have before. Okay? You have the inverter, something is going in, something is going out, and you are losing in between. Okay? So what is going out is U A C E A A C. Okay? Alternative. And then what is going in is U DC I DC. So it is 201 multiply 15.1 divided by 253 multiply 14.7. And here we found 0.937. That means 83.7%. The manufacturer was providing 93.5. So it's consistent, okay? There is no surprise. we can trust in the manufacturer. But it's good to check. Okay, we are able in each PV central. You are able to check because the inverter is providing this value, measuring in permanently what arrive, what is going out. So at a certain time you can check it. So now calculate the loss due to the rise in temperature of the PV modules. Okay. If we have not, here I give a short cut regarding the temperature because I directly give you the cell temperature. Okay. But if you have not the cell temperature, you can use the NOC correlation, okay, that will give you an estimation of the T cell temperature regarding ambient temperature, okay. So, can you give me the loss in percent due to the elevation of temperature? Elevation of temperature compared to what? To 25 degrees, okay? Due to rise in temperature, compare to 25 degrees. Instead of 25 degrees, we have Tc is equal to 50 something. 50? What I give you? What was the temperature I give to you? 50, no? 55?
Operating temperature.
For the cell temperature?
55.
55. Okay? That means that instead of 25 degrees, which is Tc in standard, configuration, we have 55. So we have 30 degrees of difference. So it is 30 multiply okay. And here we find minus. So we will lose, as we are losing 0.43 per degree, we have 30 degrees of difference. We lose at that time, precise time, 12.9%, 13% of the power. Okay, you see that you can feel the importance of the temperature. What is the theoretical power that should be produced by my central?
After considering this.
Hmm?
After considering this.
No. Now I just compute some indicators, some metrics that are interesting for my operating condition. But now I start, without any consideration, what I should expect from my PV central.
Sixty-eight 68.9%.
Here?
The theoretical efficiency.
Ah, No, not theoretical. This is the theoretical power.
This is 50601.
Hmm?
50601.
No. No, 506 kilowatt is power,
By the PV.
yes, but under 1000 watt per square meter. We have 506 kilowatt if I have 1000 watt per square meter. But we have 830. Okay, so what is here? The power. The power is theoretical because I have not 1000, I have 800, and so the theoretical power is, I make a cross product, okay? This multiplied by this, and this multiplied by this. So multiply by,
8.4.
okay,
265.
divided by 1000. Yes, yes, it is so 4, 2, 6, 5. Kilowatt. So it is P. Okay. So this is just related to the solar radiation. Okay. If I was at 1000 watt per square meter, regarding my the power, that will be 5.06 kilowatt, without considering the effect of temperature. Okay, so we are not at 1000, so it's lower, but the theoretical should be that. But of course, if we consider the temperature effect, it's not the case. We will have P2. Okay. So can you give me P2, PE2?
4480. 4480.
No,
Less than
less. I have 3 dot something.
0.26 into 0.129.
You have to, compare to that, you have to consider that there is minus 12.9% of power.
3.71.
Yes. Okay, here it's without considering the temperature. Now, I'm considering the temperature effect, and I see that the power will lose 12.9. Okay, so P2 is equal to P1. So it is j'en suis. Okay. So while considering both that I am not at 1000 watt per square meter and I'm not at 25 degree. Okay. Now I ask you what is the power. So this is considering both radiation and temperature, which are not standard condition. Not at 1000, not at 25 degree. Okay. Now I told that I want to consider that there is around 1% of loss due to cable. Okay. So, of course, it will decrease again to consider that. So it will be PE2 multiplied by 1, 0. Yes, is it? So you will find 3.677 kilowatt. Okay. Now it's not finished because we have to consider the efficiency of the inverter. Okay. We see that it is not at 25 degree. It is not at 1000 watt per square meter. There is loss due to cable. There is loss due to inverter. Hmm?
Inverter efficiency 93.5%.
Hmm. So what do you find for P3, P4?
3.437.
I find 3.445. In principle, we should have the same result. Huh? I take the right. I took that. Yes. P4 is equal to P3 So we find 3.445 kilowatt. Is there some mean to check I have no committed some error in my computation? There is one mean to check that there is no error in my computation. Or it could be error in my computation, or it could be that, for example, the cables are not generating 1% of loss, but maybe more. Okay. I give you an assumption about 1% of loss due to cable, but there is one mean to check if this assumption is good or there is a problem. Okay. So what is this way to check? To compute another power, which is PE5. Which is the power after the inverter. I'm able to compute this power after the inverter. What is the value of this power? Depending of the measures that I have made. It is a power that I can extract from the measure of the voltage and intensity after the inverter. So 231 and okay. And in principle, I should not be far from this while considering all the loss, including the inverter. Okay. So here, if I compute that, I found 3 dot. So you see, it's not so far. That means that my assumption about loss in the cable is not so bad. If I was far, it's a mean to check that this may be a problem. Okay? So when I was presenting Heliocity, it is one of the things that it is constantly check. Okay? Power which is extracted from the data after the inverter and considering all the loss. Okay? And if the discrepancy, that means that maybe one cable is cut or one cable is overheating because there's too much Joule effect or things like this. Okay, it's a way to check if it's full consistent. The fact that we have not 1000 radiation but 843, so the power is lower, is not a problem. It's consistent. The problem that we consider the temperature and the power is low, it's consistent. Okay. The cable that we estimate at 1% in loss, this is a way to check that the assumption is not so bad. Okay, the cable seems to be okay. We are not far. Maybe 1% is too much, because here you can see the power that we identify while considering all the is a bit lower than the real one. This is the real one. So that means that probably the loss of the power in my cable is less than 1%. So it's better like this. Okay, it's a mean to check. So P4 and P5 are quite very similar. So that means that the installation seems to work fully good, in a good condition. Okay. Now we will compute the performance ratio. So what is the performance ratio? This is, I forget, there was a 5 here. So how can I compute the performance ratio? So it is to have a global evaluation of the performance of my PV central. Okay. So, of course, it is a ratio between two power, which one divided by each one. But it is what I can expect. It is the maximum. So the maximum will be here. That's what I have in reality. In reality, I have that. And tell me if it's well or not.
81%. 81%.
Yes. So, yes, you're right. So I have 0.117. So it's over 0.8. I said that if it is at 0.8 or over, it's very good. My PV central is operating in good condition, no problem. If it is lower than 0.8, maybe it is too hot because it's integrating in a building, so it could be 0.75, maybe zero other thing, soiling, okay. So this is over the 0.8, it's okay. So PR is an efficiency, okay? Another way to compute PR, it is, when you have a lot of different efficiency, what is the final efficiency? I know 80%, then after I have something, 10%, then I have something, what is the final global efficiency? It is a multiplication of all this efficiency, okay? It is N1 multiplied by N2 multiplied by when there is many efficiency following, okay? So it's another way to compute it. So try to compute considering each efficiency at each step, okay? And in principle, you should not be far from here. it's also a way to check that we don't make a mistake. So you see how to do. First, you have the temperature effect. So it was 1 minus efficiency linked to temperature effect. Then you have cable loss. It is 1 minus, we said 1%, okay? And finally, you have the inverter, okay? Okay, so two ways to compute. What I have finally as a power, what I can expect. Or the other thing is, when you have a kind of cascade of transformation with each time an efficiency, the final efficiency is a multiplication of all the efficiency. Okay, so this effect of temperature, cable, inverter, and in principle you should not be far from this. And if I do that, I will find 0.807. Okay, so compared to that, it is very close. Why it is not exactly? Because I told you previously that there is chance that my loss due to cable is under 1%. So yeah, I find more because in reality, the assumption that I've made that 1% of power was lost in the cable is not really true. It's a bit lower, which is better, okay? Whereas here it's considering all my efficiency and this assumption here that it is 1%, but in reality it should be less than 1%. I can exactly identify this percentage compared to that, okay? If I say that is equal to 0.817, what is this value here? I will find, for example, 0.007, so 0.7%, okay? To find the exact value of the, and that will give me an estimation of the exact loss due to cable. It's a way also to analyze that. Is it clear? Okay. So it is the performance ratio. I should have given some other question after. Can I change? Okay, well done. Now, given the sun exposed surface, so we have 44 PV panels for a surface of 45, so it's almost 1 square meter per panels. What is the theoretical conversion efficiency of the generator at 1000 watt per square meter at 25 degree? So do we have an idea of the range that we should find? So PV conversion of my PV central finally could be around up to 10 to 20, depending on the technology.
11.24.
Yes. So in theory, I should produce what arrive on my panel. It's 45. Sorry. Yes, it's yes. Okay. Theoretically, what arrive on my panels in standard condition. And so the efficiency of my PV central it is what I can expect theoretically. So with my power, I can expect that. And compared to what is arriving, okay, so we find 0.112. Okay. So that means that 88 only one. So 88.8 are lost. They are coming, they are collected but not converted. Okay. Okay. So now we have this per month, so it's more what we used to exploit till now. Okay. So January, February, March, and this is a year scale. Okay. We noticed that the electrical production in January was 227. We ask you to compute the performance ratio for each month. Okay. and to identify when is the minimum, when is the maximum. So can you complete that?
January this 9.5 points.
For the first one,
9.5.
no, I have 0.84. The area of the solar PV, it's 45.
Yeah. 53 multiplied by 445
Mm-hmm.
E divided by 55 times area
Mm-hmm.
will be 9.5%.
Did you consider the efficiency of the conversion?
Efficiency. That's efficiency.
Because not all it should be converted. I have not the detail of my computation. Okay, so how do you proceed in the simplest way? Somebody find this value. Somebody else find?
Yes, sir.
You can come for one demonstration.
Yeah, we got it.
If you find it. You go for one for the first value. So for January, so can you explain what you...
This is the solar radiation in 1 month.
Incident radiation?
Yeah. Then this is the area,
Yes.
and this is the efficiency of solar panel. So that 268. No, 68. Fine.
What?
268. About 268 we get.
Mhm.
And then we divide it 2 to 7. Divide here. 27.
Divided by how much?
268. That one. So performance ratio will be 0.847.
4, 7, yes, okay. Mhm. Okay, thank you. So it's a way to evaluate, yes. In principle, we should have that, okay, but we don't have that. So the difference is due to the performance ratio for PV central. And so it's like this that we estimate the performance ratio per month. Okay. Otherwise, it's not easy to see if in July it operates well or not, because the sun radiation is all the time different. So we don't know if that is consistent with that is consistent with that, because looking like this, the irradiation is all the time different. So we have to consider something common, okay? So what we can see from that is that we are producing more, okay? We are producing more during summertime, much more. Okay, you see here, 726 kilowatt hour during July month. So we are producing much more than in January, but the PV central operates in a bad condition compared to the winter time. Okay, we're producing much more, but the performance ratio is less good than in winter time. Okay. Why it's less good? Because of temperature. Temperature is higher. Okay. So we can see that a PV central will produce more in sun day because the days are longer and there is more sun, but the performance is less globally because here the temperature could be also linked to the soiling or thing like this. Okay. So it's this performance ratio is interesting, very interesting to see if the PV central is operate or not in good condition. Okay, so the performance ratio on the whole year could be on the year is equal to 6,305 kilowatt hour divided by what is coming what could be expected. And this is 0.1. Global electrical production. Electrical annual electrical production. Energy for a year is equal of 6 kilowatt hour. Okay, it is that. How many hours per year the PV central is operating in the power peak condition? So it is the total of the production divided by the power peak of my central, and it will provide 1,206 hours. It looks like if my PV central was operating during 1,246 hours at my power peak. It's not really the case, but just to have an equivalent, how many hours per year I can consider it will operate in a maximum power factor. Okay? Do you have any question?
What is the actual formula for the performance ratio? Means, it is sometimes mistakenly can be write as efficiency, and sometimes it is different. That's why.
No, you have two kinds of efficiency. You have the efficiency of your PV panel. Okay? So this is independent of the performance ratio. You have a certain amount of solar energy coming on your PV central, and you know that only 12, 15, 16% will be converted in electricity. It is efficiency of conversion. Okay? But the performance ratio is the efficiency of the global PV central. Okay? So that we don't consider the efficiency of the conversion finally, because it's already known that we will not have more than 15% because of this panel. Okay? So it's not a problem. It is linked to the panel, which is not able to convert more than 15%. Then starting from this, we look at all the stage where we could have this power, but we have not this power until the injection on the grid. Okay? And it is this whole chain that considers the performance ratio. Okay? The performance ratio don't consider the efficiency of the performance of my panel. It is done like this. It is a cell like this. You are buying a panel you have an efficiency, okay? So you can't increase that except if you change your panel. Okay. So the performance ratio is when it is integrated, what you should expect and what you are really at the end. Okay. So this is the performance ratio. It is the efficiency of my PV system. Okay. And it's different than the efficiency of my PV panels, because when I buy these PV panels, I know that limitation.
You can actually control this.
Yes, it's normal. The photo conversion efficiency linked to a PV panel is normal. It's cell like this. You can't change it. But what you can change is that there is a problem on your PV central. Cables that are inducing more than 1% of loss, soiling that you will decrease. You are expecting that for such a sun, you should have this, but you don't have it. But maybe there is soiling that reduce incident radiation and things like that. So the performance ratio is characterizing the operating condition of your PV central, if it is well or not. Okay, and it is important that it's good if it is over 0.8, 80% is good, so no problem. You don't have to check every day. If you find that it's good. If it is below, you should investigate the reason why. Typically here it is below, but we know that because the temperature is probably high. Okay. But if it is winter and you find that in winter, a problem. It could be snow on you that generates shadow on your PV. Okay, so you are, or it could be something wrong with one PV panel that is destroyed. Or okay, this in winter is not normal. Yes, or because the installation is not well integrated. So put on the insulation and it should be working better than that, and it is not the case. Okay. So it's a matrix in order to give you information of the well-being of the PV central. It's important. Okay. Because like this, if you just look at this, you say, oh wait, yes, I'm producing a lot, but you don't know if you can produce more or it is less than expected. So it's a very interesting matrix. Okay. Other question? So if you have no more question, we can conclude here. So I just want to tell you that I was very happy to spend 1 week with you. And I hope you were interested by the lecture and tutorial that we have done. And this target, the aim of this was to give you an overview of all the solar technology, to give you idea of some range of power that could be expected, range of temperature, how we can identify if a performance is okay or not, what the range of performance also for regarding the use that you need after different technology. So it was quite dense, but I hope that you have learned things and it was interesting for you. Thank you.
So it's a very interesting session, right? So everyone participated, and now you know how to investigate the performance of a solar PV power plant. Okay, how this temperature plays an important role. Even though we think that in summer it will work best, but not. It's winter. But at the same time, we need to check if this cloud cover and then maybe what is called snow is covering.
Yes.
Then again, we will not get that much of radiation. That is also important. Okay. So thank you for your presence, and please come at 2:30 sharp. We'll start today, not 3 o'clock. It's 2:30. So you have to quickly take the lunch and come back, right? Okay, then see you at 2:30. Thank you.